Today we are of 2011 Nationals. We are on team number 10. So we have three real numbers, a, b, and c, satisfy the equations a plus b plus c equals 2, ab plus ac plus bc equals -7, and abc equals -14. What is the largest of the three numbers? Express your answer in simplest radical form. Okay, so for team math counts, you're allowed a calculator, and you're allowed up to like a CAS calculator. So CAS calculators are allowed. And so if you have a CAS calculator, this is just three equations, three variables, and you can just plug it in into your CAS calculator. So all you have to do is have a calculator page open, click menu, click 3 for algebra, click 7 for system of equations, and then click 1, and then put the number of equations as 3, and then click enter. And then you can put three equations in, but put it in X, Y, Z, and instead of ABC. And then it solves it for you, and it gives you like a bunch of like X equals this and Y equals this and Z equals this, or X equals this and Y equals this and blah blah blah. It's just saying that because X, Y, Z are interchangeable here, so it's gonna give like all six of the permutations of it. But you can just like take one and find the biggest. And if you do that, then you see it's root 7, and yeah, the answer is just root 7. So basically, if you're doing math counts, well, if you already have a CAS calculator, then you definitely want to bring your CAS calculator because it's very powerful, and it can help you a lot on team and target. Um, if you don't have a calculator or CAS calculator, I think we would highly suggest you to get one because I don't know, the CAS calculator can be used on various um, contests. So it can be used on math counts. Can it be used on like SAT? Do they let you bring your own? Do you know, Bill?
On the SAT, I'm actually not quite sure if CAS is allowed. I know the normal
Okay.
Inspire is allowed, but I'm not sure about CAS.
Okay, but yeah, I like a lot of various stuff allows CAS, right? Or like
I'm
or
pretty sure
UIL
generally
allows.
like they don't even check. I've brought my CAS to the PSAT before and they never said
Or
anything
that
about
was
it.
just like the practice PSAT, so they might have been
Well,
like not
that was
really
a that
stringent
was
about
that was a real PSAT though. So
maybe I don't know.
yeah.
But yeah, I mean you could also use CAS on like calculator and math UIL. That's just like in Texas, but also you have like AP tests, right? Like AP stats, you can have CAS, AP calculus, you can have CAS, um, and yeah, and generally, I mean, you know, it, it's a calculator that you can use for various things.
By the way, when we say
So
CAS, we mean like the TI Inspire CX CAS, not
yeah,
like the other
that
ones.
specific model.
Yeah.
Yes. So if you like, especially if you don't have like any calculator yet, we would suggest you to get this model, which Bill just said. Basically, like, yeah, it's very powerful, and you could use it in a lot of places.
It's
Um,
kind of like I'm pretty sure it's like the most powerful calculator allowed on like most standard tests, most like tests and competitions and stuff, where calculators are
yeah,
allowed.
yeah, or at least like one of the most powerful. But yeah, but if you don't have a CAS, then so like only CAS calculators can solve like non-linear system of equations, I believe. That's what Bill said. So if you don't have a CAS calculator, and you're not going to get one, then for this one, I I think you would just kind of have to use Vietas to put this into a cubic equation and then graph the cubic equation on your calculator and then find the roots of that graph. Um, and then yeah. So like if you yeah, did you want to say something?
Yeah, and like Vietas on like this problem isn't very hard because all of the values for Vietas are already given to you. So like there's not really much you have to do to make this into a cubic function.
Yeah. Yeah, you can see that this is already in like Vieta's form. So if you have the sum, it's two and it's on a cubic, then the or so I'll just have so x cubed, I'm just gonna have it as a coefficient of one. And then if the sum of the three roots is two, then the second coefficient has to be negative two. And then if the sum of the roots taken as a, or the sum of the product of the roots taken two at a time is negative seven, then this coefficient will be negative seven. And then if the product of all three of the roots is negative 14, then this coefficient will be 14. So then this will be the cubic equation, and the roots of this cubic equation will be the three real numbers satisfying these three equations. So then you can graph this and find the roots or find the largest root, and that can also work. But yeah, if you are looking to get a calculator, then we suggest you getting the CAS, and it's very easy just to do this on the CAS. Okay, anything you want to say for that, Bill?
Um, so do you want to talk about how you would do this without a graphing calculator? Like,
Uh, well, then you just had to solve the cubic by hand, right?
yeah, I guess you just solve the cubic by hand, which,
Um, I mean, and then I mean, it's not that great, but I guess you could use the rational root theorem. So, you can deduce like which roots you can try to like um, 1, 7, 14, and negative 1, negative 7, negative 14, also 2. But then like you have to try two or sorry, 8 roots by hand. Or I mean, or using the calculator. But yeah, that's still slower. So yeah, you would try all these roots by the rational root theorem, and then if you find one that works, then you synthetically divide, and then you get a quadratic, and then you solve the quadratic. But that's much slower than like any of the other stuff. Like I feel like if you don't have a graphing calculator at all, I think I would suggest you to get some sort of graphing calculator, right?
yeah, having a graphing calculator is like provides like a massive advantage in like these tests.
Yes. Also, I think we need to include the rational root theorem on the doc.
Yeah, but we can include it later.
Uh, wait, just give me a second. Okay. Okay, so that's it for 2011. And so now we're going to move on to 2010 nationals. And we're just starting on sprint here. So first we have number one. In the figure shown, the ratio of BD to DC is 4 to 3. The area of ABD is 24 square centimeters. What is the area of ADC? Okay, so um, you can solve this in multiple ways, I guess. Um, but I feel like the easiest way um, is just noticing that the two triangles share the same height. So if you look at ABD, um, this is triangle ABD, right? So if you're calculating its area, you can use like this height and this base, right? Um, so let's just call the height like random h, and this is just BD, or I don't know, I'll cut this x and I'll call this y. Okay, and then if we're looking at triangle ADC, which is this triangle right here, to calculate its area, you could also use this same height h, but you would instead use the base of y, right? So then you can see that the ratio of area of triangle ABD, or I can put it like the ratio of the area of ABD to ADC will be the ratio of x to y. And then with this, it says that the ratio of x to y is 4 to 3. So then ABD to ADC is going to be 4 to 3. And then it said ABD was 24, and we need to solve for ADC. So then, you can put ADC over here, and then you can divide by 4 on this. So then you have 6, and then you bring the 3 here. So then ADC is just going to equal 18. Um, yeah, the answer is 18. Um, so, you can also see this if you just say like, you can see this relation if you also like actually model the equations of the areas of the triangle. So you said like ABD is, or the area of ABD is 1/2 times h times x, and the area of ADC is 1/2 times h times y. And then then you can see that the ratio of the areas is just going to be the ratio of x to y, since the 1/2s and the h's cancel out. What you can also do is you could just set like x and y to something random that still satisfies the ratio, like 4 to 3, because like this problem kind of like allows that, I guess. And then you could like solve for this height with the given area. So so you could say like 1/2 times h times 4 is equal to 24, and then this would mean h would equal 12. So then you could say this is 12, and then because this is 3, then you can just solve for the area. You could say the area is then 1/2 times 12 times 3, which is an 18. So we get that again. But so like you could do that, or you could just solve it more generally with like the ratio of the stuff. But yeah, anything you want to say for that one, Bill?
I think that's pretty good. Yeah, just
Bill?
like oh, my bad. But yeah, I think you said it pretty good. Yeah, just like if the height is constant, the proportion is just based on the length of the legs, length to the base. I mean, that's just how
Yeah.
like the area of a triangle is calculated. So yeah.
Yeah, okay. Okay, so now number 2. The lattice shown is continued for 9 rows. What will be the third number in the 9th row? Okay, so we just have like rows of numbers, and each row has 5 numbers. So you can see that, if each row has 5 numbers, then, after the 8th row, after the 8th row, 40 numbers are already going to be written down, right? Um, and then so that means my starting number on row 9 is going to be 41. And then if my starting number on row 9 is 41, then I can just count up to find the third number in the 9th row, which is just going to be 43. Um, so yeah, I don't know, this is pretty easy. You could also just model what the third number in each of the rows is, because it always increases by 5, right? So then it has to be like an equation of 5x, and then you just take row 1, for example. So you plug in x to be 1, so then you have to have a -2. So then you can just model the third number in each row as 5x minus 2. So then you just plug in 9 and that gives you 43 as well. And then you see that the answer is 43. Okay, so anything you want to say for this one, Bill?
Um, I mean, it's pretty simple. There's not really much to it.
Yeah, okay. Simone has placed 18 dimes in a row on the table. Always starting from the left, first she exchanges each third coin for a quarter, then she exchanges each second coin for a nickel, and finally she exchanges each ninth coin for a penny. In cents, how much money does Simone have after the final exchange? Okay, interesting. You could work this out by hand, but I wonder if there is a better way to do it. Um,
Well, it's 18. It's only 18 like coins, so it's not that much.
that's true. But you could also, I guess, so like just write out like all the coins. Like don't like calculate like the money that you have in like each step. Like calculate how much money has changed. Because then like you I don't know, that's just gonna be like
Yeah,
more work. What you
yeah,
can
just like
instead do is just
have the
change all
coins.
the coins and then add up all the coins at the end. And I guess yeah, it's not too bad because you only have 18 coins. Yeah. Okay, so I guess we'll just do that. So we have a bunch of dimes. That's 6. This is 9. It's 3. This is 3, and then this is 3. Okay. And then we're gonna exchange each third coin for a quarter. And I'm only gonna write like these new coins, so I don't have to write like all the dimes again. That would just kind of be redundant. So I'm basically just gonna like stack these on top of each other, and then whatever is at like the very bottom for each column, that's gonna be the coin I'm gonna use at the end. So and then I have each second coin, exchange it with a nickel. So boom, 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 boom. Okay, and then finally I exchange each ninth coin for a penny. So this was my 9 right here. So that's gonna be a penny. That's gonna be a penny. Okay, so now I can just add all this up. So again, I would take the last coin that occurs in each column. So this one I would take dime, this one I would take nickel. So I would take quarter, this one I would take nickel, this one I would take dime, and so on. So I'm just gonna oh wait, this is sprint, so you don't have to calculate. But yeah, I mean it's still not that bad. So dime is 10, so nickel we have 15, quarter we have 40, nickel we have 45, dime we have 55, nickel we have 60, dime we have 70, nickel we have 75, penny we have 76. Those are in line. And then nickel we have 81, dime we have 91, nickel we have 96, dime we have 106, nickel we have 111, quarter we have 136, nickel we have 141, dime we have 151, penny we have 152. So then our final money should be 152. It just wants it in cents. And yeah, that's our answer. Anything you want to say for that one, Phil?
Um, well, like you drew it out. I don't think you necessarily have to draw the whole thing out. Like, um, you could you could very well just say like first there first you'll end up with 12 dimes and 6 quarters. And then after you change the nickels, you'll end up with 9 nickels, and then like it'll be 9 nickels, and then it will be 3 quarters, and then the rest are dimes. And then for the pennies, you'll be switching out 2 of the quarters for pennies. like that.
Yeah. Well, yeah. Yeah. If you can just think about it like that, you can do that as well. But if you also need to draw it visually, you can also draw it visually. And also, when you add this stuff together, you also don't really have to like count all this. You could also just like start with the base, like all of the dimes, which is gonna be 180, and then you're gonna like subtract or add depending on what the coin you're actually taking is. So like for this one, I would need to subtract 5 because it's actually a nickel and I said it was a dime. And then for this one, I would need to add 15. And then so that's just, I don't know, like a little bit quicker. Like you don't have to go through all of them, I guess. But yeah, I mean, it's still not that bad. Okay, next question.
Yeah,
Oh, it
like
had a
this
picture
way,
here.
and like this way it might be like slightly more expandable in case you're
Oh,
going
well, if
beyond
it,
18. If you're going like beyond like a number that you can't actually just like physically do, like you can just like, because essentially all I did was like divided by 3, divided by 6, divided by 2 and stuff like that. So, yeah.
yeah, yeah, that would be better, like if you had like really large numbers, but I mean 18 is still doable if you
Yeah,
just like
18 is
listed it
doable.
out. But it also gives you a picture here, so and like when you take it, you'll do it on paper. So um yeah, you could also just use this as a model. So then you don't have to write out all the d's and stuff. Okay, number 4, the value of the numerator of a particular fraction is one half the value of its denominator. If the numerator is increased by 2 and the denominator is decreased by 2, the value of the resulting fraction is 3/4. What is the denominator of the original fraction? Okay, so first we had the numerator of a particular fraction is one half the value of its denominator. So let's just say, the original fraction, the denominator is x, so then the numerator will be one half x. So this is our original fraction. And then it's saying if the numerator is increased by 2 and the denominator is decreased by 2, then the value of this resulting fraction is 3/4. We want to know what's the denominator of the original fraction. So we want to know what x is. So now we just have this equation and we need to solve for x. And it's sprint, you don't have a calculator, but it's just a pretty simple linear equation solver. So we're gonna cross multiply on both sides. So we're gonna get 2x plus 8 is equal to 3x minus 6. So then we have x on this side and we have 14 here, x just equal to 14. And yeah, that's your answer. Pretty simple, I would say. Margaret is constructing a square dartboard. It will consist of a smaller square centered in a larger square. The smaller square measures 4 inches on each side. The ratio of the area of the smaller square to that of the entire dartboard is 4/9. How long is the side of the larger square? Okay, uh, wait, what? Wait, it won't let me. Wait, it won't let me
Move the what?
move the. It won't let me draw either. It's just not responding.
Oh, what? Is it Illustrator itself? Is it the tablet's fault or the thing's fault?
Oh, it's working now. Okay,
Okay.
that was weird. Okay, I don't know. You could draw this if you wanted to. Um, so you have a smaller square and a larger square. Smaller square is 4, and it says the ratio of the area of the smaller square to the entire dartboard is 4/9. And how long is the side of the larger square? So if you have so we said this a lot, but like if you have the ratio of area of 2D shapes and they're similar, then the ratio of like any 1D property of them. So in this case we're looking at the ratio of their length, and that's 1D. So that's just going to be the square root of whatever their 2D ratio was. So that means that the ratio of this length to this length is then going to be the square root of 4/9, which is going to be 2/3, right? So then you just find that ratio, and then this is just going to be 6. And yeah, that's your answer. I don't know. You really don't have to draw it out. You could just think like, you know, if the area of a square to another square is 4 nines, then the side ratio is going to be 2/3. And if this is 4, then I'm just going to multiply 3 halves by 4, and that's going to give me 6. Yeah, anything you want to say for that one, Bill?
I mean, yeah, this concept comes up a lot of like just proportions between like one-dimensional and two-dimensional, and then like three-dimensional. But
Yeah.
yeah, I think we'll use it like even later in like this 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 later in sprint. Like we'll use it today. I think.
Oh, wait, we had a question for
Yeah, we
that?
had a question like
Okay.
that uses this.
Okay, well, yeah, this is fairly common. Yeah. Okay, number 6. Friendly Tyler's charges $75 per delivery and $43 for each hour worked. Tiles RS charges $60 per delivery and $45 per hour worked. Assuming one delivery, what is the greatest whole number of hours for which Tiles RS is the cheaper option? Okay, so this is just like a model of, you could put the money that they charge as a model of time, and it's just going to be a linear equation. So for friendly tilers, um, they charge 43 hours per hour worked, and let's say the number of hours they worked is t, and they also have a $75 delivery charge. Then this is going to be the equation modeling how much they charge. And the tiles RS is going to be $60 times t. No, sorry, it's going to be $45 times t plus $60. Um, and yeah, you're going with one delivery, and you want to know what is the greatest whole number of hours for which Tiles RS is the cheaper option. So Tiles RS is this one. So basically, we want this one to be less than. So we want this one to be greater than, this one to be less than, and we want to find the greatest value of t that satisfies that inequality. So then we're going to solve for that. So we're going to bring 43t onto this side, so then it would be 2t, and then we bring the 60 onto that side, so then it's going to be 15. So then it's saying t has to be, or sorry, t has to be less than 15 halves, which is 7.5. So t has to be less than 7.5, and we're looking for the greatest value of t as an integer, or a whole number, sorry. Then it's just going to be 7. Um, and yeah, we see that's our answer. I think it's pretty simple. A set of 11 distinct positive integers has a mean of 8 and a range of less than 12. What is the largest possible integer that could be a member of the sets? Okay, interesting. So, hmm. Well, first we're gonna want first we're probably gonna want the range to be as large as possible. And what we're gonna want to do is we're gonna want to make the 10 oh, okay, it's also distinct. You want to make the 10 numbers, the 10 other numbers, as small as possible. Um, so that the other number can be large, but it also can't exceed a range of 11. Hmm. So this is going to be limited on what we set our smallest number to be, because whatever our smallest number is, that sets like a higher limit on what our largest member of the set can be, right? So first imagine the set to be like listed in order, right? So we're gonna have 10 numbers here, and then we're gonna have our largest number here. And we want to make the largest number as large as possible. So the range is gonna be the difference of our smallest and our largest number, right? And we're told that, at largest it can be 11, and we're going to want it to be the largest because, we want to make all this as small as possible, and we want to make all this as large as possible, right? So we're going to want the range to be as large as possible. We're going to say it's 11. So this is 11. If we want this to be as large as possible, then whatever our smallest number is gives a bound to what the largest number can be, right? So like if our smallest number was 6, then our largest number can only be as big as 17. Um, so kind of like we want our smallest number to be as large as possible so that our largest number can also be as large as possible. And so I would say, you could try like finding what values of like your smallest number that you can have. So like you can't have 6 because if you had 6, then your 10 numbers, they all had to be distinct, right? And this is the smallest number, right? Um, and then there's no possible way of having all of this as a mean of 8, right? Even if we had all the other numbers be as small as possible, which would be 7, 8, 9, 10, 11, and so on, you can already see that this is gonna like way exceed the mean of 8, right? Because like this is 8 right here, and they're gonna be a lot more larger numbers, and this is also gonna be a larger number, and so this is not gonna have a mean of 8, right? So we had to lower this quite a bit. So maybe try like 4 or something, right? So if we have 4, then our 10 numbers can be 5, 6, 7, 8, 9, 10, 11, 12, 13. This is also not gonna give a mean of 8, right? Because 8 is right here, and there's 5 numbers on this side, and there's 4 numbers on this side, and we also have another number over here. So this is not going to give us a mean of 8. So we have to lower the lowest number again. So now we try 3. So if we have 3, then we have 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13. Or not 13, sorry, just right here. And then you can see that it's possible to have a mean of 8 now, because all of these would cancel with each other if we're finding the mean, and then we have a small number here and a large number here. So then, then we could just find what the large number is here by finding the distance the smallest number is to 8. So the smallest number is 5 away from 8. So that means our largest number will have to be 5 away from 8 as well. So then our largest number has to be 13. And then we can see that this could work, right? Because 3 and 13 has a range of 10, and 10 was less than 12, and our range has to be less than 12. And then, but, but we didn't utilize our full range. So maybe you might be thinking like, there could be other smallest numbers that we can use that it would give us an even larger number. But I don't know. You can see that's not possible if you like if you look at 2, which is the next largest smallest number, even if we had the biggest range of 11, then our largest number can only be as large as 13. But we already found that 13 works in this case, so it doesn't really matter if 13 works in this case or not. And as we decrease this, well, our last thing we can only have 1, but yeah, but like as we decrease this, the range is just gonna limit it more, and then it's not ever gonna exceed 13, right? So with us finding 13 here, we can see that's gonna be the biggest solution that we have. So then, yeah, our answer should be 13. And yeah, it is 13. Okay, anything you want to say for this one, Bill?
I mean, it's when it says it's like a set of 11 distinct positive integers, and the range is less than 12. That makes it pretty obvious that like it's 11 consecutive numbers. So, I mean, like, yeah, 11 consecutive numbers. Like, if you have more than 11 consecutive numbers, if there was like one number that wasn't consecutive, that's like, hmm.
Oh, wait.
I'm not quite sure how I want to say this. Mm, I mean, I guess your method was fine, I guess. But I mean, it's pretty easy to see that, it's like pretty close to being just that. It's like 11 consecutive numbers. So it's like 8 is like very close to the middle of the path of like the 11 numbers. 8 is going to be like very close to the middle. So you can kind of just like make an assumption and like work from there, I guess.
Um, yeah, well, so like extending on what Bill said, you know, if you so it says that the range is less than 12, and like if you think of your like 11 distinct positive integers, even if they were like most compact as possible, which would be that like if they were all consecutive with each other, then the range would already be 10, right? So then you can see like either they're going to be all consecutive or like there's going to be one like jump in between, one jump in between of a length of one, right? And that would just make it a range of 11, which is also possible, right? But you can also see that like um, it has to be uh, consecutive, right? Because like if you have 11 consecutive numbers, um, wait, um, no, actually, okay, well, okay, actually, no, yeah, then you just have like the cases of either they're all consecutive or there's like a one gap in between. So Um, yeah, and well, and like 8 is going to be somewhere close, so close to the middle. So then I would just like test that, I guess. So like I would put like 8 in the middle, and I see if like all of them being consecutive would work, which it does work. So then I would just go with that. But like if it doesn't work, then I would just look at like how I could put the one gap in between and stuff. But yeah, that is I would say a faster way to do it. So yeah, noticing that would be helpful for this problem. Okay. Base prime representation of a natural number is defined using the exponents of its prime factorization as follows. Each place in a base prime represents a prime number and it is occupied by the corresponding exponent of that prime, starting on the right side with the smallest prime number and proceeding to the left with the largest prime number. For instance, since 84 is equal to 7 to the first times 5 to the 0 times 3 to the first times 2 squared, then 84 would be written as 1012 in base prime. What is 225 written in base prime? Okay, well, like it basically tells us it tells us all of like what base prime is. So then we just have to apply like this prime factorization stuff onto 225. So this shouldn't be too bad. So just reading it again. So you're gonna prime factorize it, and you're gonna you're gonna put the left side with the largest prime number factor that your number has, and then you're gonna have to list out all of the other primes in descending order, and then you put their exponents on top, and then you just take all those exponents in order. So we're gonna want to look at the prime factorization of 225. So we can take out a 5, and then we're gonna have 45, and we could take out another 5 from 45, and we're gonna have 9, and 9 is just gonna be 3 squared. So the prime factorization of 225 is 3 squared and 5 squared. Um, and so our largest prime is going to be 5. So we're going to have 5 squared here. And then we're going to list out the other primes that are smaller than 5. And then, it's just 3 and 2. And 3 was the exponent of 2. And we had no 2's. So then our base prime is going to be 220. Yeah, that's your answer. Um, I don't know. Anything you want to say for this one, Bill?
I mean, as long as you understood the question, there's not really anything complicated about it.
Yeah. Okay. Number 9. Billy, what? The quality of that image is so bad. Okay. Billy is hiking in Colorado. He walks eastward 4 miles, then turns 60 degrees northward and walks 6 miles. How far is he from the starting point, especially answering so this one? No, what is the reasoning of having this picture here?
Not sure. If you look at number 10, there's no reason for that picture either.
Number
So,
10. Yes.
it looks
No,
cool,
yes, it just
yes.
looks cool.
It looks cool.
Very good
Exactly.
quality, I would say.
Very good
But
quality.
what is like this white gap here?
Where?
Right here. Like I thought like he was standing on like land, but then there's like I
I
don't know.
thought he was standing on a log. And like that's the
Oh,
hole in the log. Like that's the side of the log.
what?
Like you know how a log is
Oh,
like a cylinder.
uh, okay. I don't know, man. Okay. So whole log. Okay. I don't know. It's not like it's okay. Whatever. So okay, just make like a bird's eye view of this, right? So like let's say this is his starting point. He's gonna walk eastward 4 miles. So let's put this as 4. And then he's gonna turn 60 degrees northward. So, if he's facing this way, which is eastward, and he turns 60 degrees northward, then he's gonna be like facing this way. And then this angle will be 60 degrees. So then our new line will be like this. And then you can say this is 60 degrees. And then he's gonna walk 6 miles. And then want to find what this distance is. And this is a line, right? So this is just going to be 120 degrees. And then this is just simple application of law of cosines, right? We have two sides and the angle in between the two sides, and we want to find the other side. So then, I could just call this x. Then x squared is going to equal 36 plus 16 minus 2 times 6 times 4 times the cosine of 120 degrees. 36 plus 16 is just going to be 52. Cosine of 120 degrees is going to be negative 1/2. And then we have 2 times 6 times 4 and then minus. So, this is going to cancel and we're going to have this as plus. So then we have 52 plus 24. So then x squared is going to equal 76. So then x is going to equal the root of 76. And then you have to be careful. You want to take out any perfect squares from this if there are any, but I don't think there are any. But you can check by checking 76's prime factorization. So I can take out a 2, and then I'm going to have 38. Oh, wait. No, yeah, actually, you can take out a 2. And then I take out a 2 from 38, and then I have 19. Okay, yeah. You can take out a 4 from 76, so then x is going to equal 2 square root 19. And yeah, that's our answer. Anything you want to see for that one, Paul?
Well, alternatively, you could just find like how far he traveled east and how far he traveled north. So like here he would have traveled, what's that, 4 plus 3, he would have traveled 7 miles east. It's in miles, right? Yeah, 7 miles east, and then what is it, 3 square to 3 miles north, and then use Pythagorean theorem on that.
Yeah, I mean, well, I mean, there should be like a lot of ways you can do this. I mean, yeah, it's just like simple triangle stuff, but yeah, like any way you can think of doing it, it's probably fine. Yeah. Okay. What is the probability of rolling six standard six-sided dice and getting six distinct numbers? Express your answer as a common fraction. Okay, so um, one way of doing this is you can just think of like rolling each die and seeing like its probability of keeping everything distinct, I guess. So like if you think of the first die roll, no matter what it is, it's gonna be fine so far, right? It's not gonna conflict with any of the other dice, right? So the probability of the first die keeping everything distinct is just gonna be one. And then once you roll the first die, like one number is going to be taken, right? And then your next dice rolls, you can't roll on that same number, right? So like for the second die roll, you can't roll whatever you rolled for the first die, right? But you can roll any other number. So there are five numbers you can roll and one number that you can't roll. So then the probability of the second die keeping everything distinct will be 5, 6. And then after you've rolled the second die, then they're going to be, we said that was distinct, right? So now we have two distinct numbers that have been rolled um, from all the six possible numbers, right? So then our third die, it can only roll four out of the six possible numbers, right? So then the probability of it keeping everything distinct is going to be 4, 6. And you can see that it's just going to be like this pattern, right? So then I'm going to have 3, 6, then 2, 6, and 1, 6. And then so I'm going to multiply all this together. Well, I can cancel this, or I can just cancel that. And then I can cancel one of these to be this. Okay, and then 6 cubed is going to be 216. And I'm going to have 5 on the top, and then I'm going to need to multiply this by 3. And then now I just have 5 over 648. And then, oh, crap. I did something wrong.
Well, you got
Is
really close. So,
really close?
well, you are only you just need to divide the denominator by half to get to the answer. So you probably just made a mistake in calculation somewhere.
I forgot to multiply by 5. Sorry, 2. Oh, yeah, I forgot to multiply by this 2 right here. Yeah, okay. And then it would have my denominator. So then yeah, then I would have 324. And yeah, that's our answer. Okay. Anything you want to say for that one, Bill?
Oh, I also thought of just like finding how many ways you can how many permutations you can like have of the six numbers, and then putting that over just six to the six.
Yeah, you can also do that. Or it would be
It
you could
would have
just do
been
that,
like
right?
it would have been six
It would be
factor
6 factorial over
over
6 to the
six to
6, right?
six. Yeah.
Yeah. And then that's pretty much like what we have here, right? One
Yeah,
is just 6 to the
essentially,
6.
yeah, that's just what you guys have there. So,
Yeah. Oh, oh. Okay. Yeah, you can also do it in that way. Okay. Number 11, the product of three consecutive odd positive integers is 7 times their sum. What is the sum of the three integers? Okay, so let's just say the smallest number in the sequence is going to be x. And then, if they're consecutive and they're odd, that means each next integer is going to be 2 higher than x if we set x to our lowest number, which we are. And then we're saying that the product of all three of these numbers is going to equal 7 times their sum. And their sum is going to be like 3x plus 6. So because these numbers are integers, that means that, the product of this side is going to be an integer, right? And the product of this side is also going to be an integer. But we know that the integer product of this side is going to have to include a factor of 7, right? Because we have a 7 right here. So that means, because these two products are equal, that means this integer product must also include a factor of 7. So that means one of these numbers must include a factor of 7, right? Now, because these numbers are odd, that means, you can only have like one of these numbers like being an odd multiple of 7, right? So either like one of these numbers is like 7, 21, or 35, and so on. Now, if you have like these numbers, I don't know, that would be pretty big. So here is you could test like one of these numbers being 7, and you can see if that works in your thing, I guess. And then like, because this side is a cubic equation and this side is just a linear equation, depending on like which side is bigger, you can see like what direction you need to go to, like if you need to make either x like smaller or larger. So like testing 7 here would not be a bad idea here. So we could test 7 to be like the middle number here. So if 7 is the middle number, then we're going to have 5 times 7 times 9 is equal to 7 times the sum, which is just going to be 21. And then the 7's cancel. And we see that 45 is not equal to 21, right? But the more important part is that we see that this side is bigger than this side, right? The cubic is bigger than the linear part. And so we see that if we increase x more, then the cubic is going to grow more than the linear one, right? So if the cubic one is already bigger than the linear one in our case, then then we don't want to make x even bigger, right? Because it's just going to make the cubic even more bigger than the linear one, and they're never going to equal each other. So that means we need to decrease x. Well, if we need to decrease x, but like one of them still has to include like a factor of 7, then the only case we can possibly have is going to be 7 on this largest number, right? So then we have 3, 5, 7, and because this is our only case, this has to work, right? But we can also test it. So we're looking for 3 times 5 times 7 is equal to 7 times their sum, which is 15. And then these 7's cancel, and then we can see that 3 times 5 is 15, and yeah, that works. So then the sum of these three numbers is 15, so that should be our answer. Yeah, that is our answer. Anything you want to say for this one, Bill?
I mean, not really. I think you covered everything I would have said, so.
Yeah. Oh, well, you can also, I don't know, this is worse than this, but like you could also expand this as a cubic and expand this as well, and like put it all into like one cubic, and then you could solve for the cubic like that. But I mean, that's just like that's a lot of work, right? I don't know. The much easier way is just to test like one of these factors of 7. You can see what direction you need to go in, and then I don't know. Testing it was pretty easy here. So yeah. And like even if you put it in a cubic, you still have to solve it by hand, right? You don't have a calculator on Sprint, so it's putting it into a cubic is not the best here. Okay. Um, okay, next problem. What is the remainder when 7 to the 2010 is divided by 100? So basically, we're looking for 7 to the 2010 mod 100. So what we need to what we need to look for is like a periodic um, a periodic sequence of the of like 7 raised to the power of n mod 100. Because like if we find like a periodic sequence, then uh basically we just need to look at what 2010 is like mod that periodic sequence, and then then we can look at I don't know what it has to be mod 100, right? So basically like what we need to do here is we're going to start with our base number, and it's just going to be 7, and then we're going to multiply this number by itself, and then we're just going to get 49, and we're going to keep on multiplying this by itself, and we always want to look at it mod 100. So we're going to multiply 49 by 7, and that's just going to be 7 cubed, right? And if you don't know that, you can just multiply it out, but that gives you 343. But we want to look at it mod 100, right? So we can just reduce it. We can just reduce this to 43, and then now we need to multiply 7 by 43. So if you multiply that out, we see that we get 21 and then 28. We add this together and we have 301, and this mod 100 is 1. And we can see that this is really good, right? Because then if we multiply another 7 by this 1, then we're going to have 7 again. And because we have the same number here now, and we're just keeping on multiplying it by 7, we can see that this is going to repeat, right? And then we've already found our periodic sequence, right? So basically what this periodic sequence is saying is that like 7 to the first is going to correspond to 7 mod 100. 7 squared is going to correspond to 49 mod 100. 7 cubed is going to correspond to 43 mod 100. And 7 to the fourth is going to correspond to 1 mod 100. And then, as we go to 7 to the fifth, correspond to 7 mod 100. And then 7 to the sixth is going to correspond to 49 mod 100. And this is going to go so on, right? Now, because we have 4 numbers in here, you can see that we just need to look at what this exponent is mod 4, and that will give us like what mod 100 it corresponds to, right? So by seeing that 5 is 1 mod 4, then we know that it has to just correspond to 7. Right? So then we can apply it to this case. We're going to want to look at what 2010 mod 4 is. And to see if 2010 is divisible by 4, we just look at its last 2 numbers, and 10 is not divisible by 4, but 10 is even, right? So that means 2010 has to be 2 mod 4. And you can also just divide this out by 4, and it's also just 2 mod 4. So then if this is 2 mod 4, that means it has to correspond to whatever 7 squared is, mod 100. So that means then it's just going to be 49 mod 100, and that's just going to be our answer. And yeah, that is the correct answer. So basically, yeah, for this kind of like, you're raising a number to a huge power, and you're looking for its mod or something, you're going to want to look of the sequence of that number raised to like integer powers, mod whatever you're looking at, and you want to look for this periodic sequence. Anything you want to see for that one, Bill?
Mm, yeah. For these, like, there's if it's like when you see like if it's too like if like the num if the year number is involved, like here 2010, it's to the power of 2010, you're never, it's almost never gonna be like you have to actually work with the number. It's always just gonna be like a pattern or something.
Well, yeah, but like, yeah, but I mean, they could also use like whatever big number, and you still also need to apply this. But just basically, like, if you just see something like
If
extremely big, this
if
like
it's
it's
just
obvious
like
it's gonna be this, like, uh,
yeah, if it's just like a big number with not really much significance, it's just pretty much there's gonna be a pattern.
but yeah, I mean, but like, I mean, I mean, it's also just like this type of thing. Like, I mean, there's only really like one way to do it. So even if you had like, I don't know, like 7 to the 6 or something, you could still just like use this. Okay. Number 13. A bag contains 3 balls labeled 2, 4, and 8. A ball is to be picked. The value on the label is to be recorded, and then the ball is to be returned to the bag. This will be done 3 times, and then the values will be added together. What is the sum of all the possible distinct sums? So basically, we're picking 3 balls from this, and they can repeat, and then it's going to give us a sum. So like, let's say we pick 2, 4, and 2. This is going to give us a sum of 8. And we want to find what the sum of all possible distinct sum is. And it's distinct sums, right? So like if we pick 2, 4, and 2 and we get 8, and then we pick 2, 2, and 4 and we also get 8, um, we still only want to count this 8 twice. Or sorry, we only want to count this 8 once. So, once we've counted this 8, no matter if we get the sum of 8 again, we only want to count it once. Um, because we have the sum of only distinct sums. I don't know. It makes this a little bit more weird, right? If we just had like all possible sums, then we could just like find like then it would be really nice. Then we could just like kind of like list it all out, but not like actually list it all out, but like each number would occur in each column like the same number of times, and we just find that number of times, and we could just add it all together. But because it's distinct, it's going to be a little bit more weird, right? Like for each sum, there's going to be like a different number of ways we can do for each sum, and I don't know, maybe there is a way you could kind of find that algebraically, like methodically, I guess, but it's a little bit weird. So instead of doing it like that, we could instead just find what possible distinct sums can happen just like by hand. Um, and why we can do that more so than like putting it algebraically, I guess, is because the range of what our sums can be is not that big. So if we pick the 2 smallest numbers, 2, 2, 2, we have a sum of 6. If we pick the 3 largest numbers, 8, 8, 8, we have 24. And I don't know, the range of 6 to 24 is really not that big, especially because our sums can also only be even, right? Since we only have even numbers to choose from. So listing out all the possible distinct sums here by hand shouldn't really be that bad, right? So yeah, we're gonna do that instead of doing anything algebraic. Okay, so let's just start with 6, and we're gonna try to just like work our way up. So if we have our sequence 2, 2, 2 for 6, the smallest difference between each distinct sum we can have is 2, right? Because all of our distinct sums have to be even. So we want to look to see if 8 is possible, and this will be possible, right? Because we can just transform our 2 into 4, right? And when we transform our 2 into 4, we're going to add 2 to our new distinct sum, right? And then we can see, you know, 42 is going to be 8. And then from that, we can also transform that 2 into a 4, and that's also going to add just 2 to our sum, right? And that's also going to, get our next smallest possible distinct sum. And we can also move this 2 up by 2, and that's also going to give us 12, right? So far, all these worked, and that's going to be, we've gotten all the possible ones from 6 to 12, right? Now you want to see if 14 works. Um, I don't know. I feel like you kind of just had to test that out a bit. But you can see that 2, 4, and 8 works. This adds up to 14. But I don't know. Like testing it out really isn't that bad. Yeah, you can pretty easily find that this is just going to equal 14. So then we see also that 14 works here. And then for 16, we could also push this 2 up to a 4. So that's also going to increase it by 2. So we're also going to be able to get 16. And then 18, 14 was 2, 4, 8, right? We can push, so instead of doing this, we can push the 4 up to an 8. So you push the 4 up to an 8, then that adds 4 to our number. And so we can push our 14 up to an 18. So then we also get 18. So far all of this works, and they're all 2 apart, right? So that means we surely like didn't miss any distinct sum here. Okay, now we're getting close to 24. Now our only possible ones left, or our only possibly possible ones left are 20 and 22. Now, if you look at 24, 24 is 888, right? Um, and if you want to make this like, if you want to like um, decrease this, but like make it as large as possible, um, then you would just have to decrease this one of these 8s by 4, right? Um, and then this would give you like the next largest sum that you can get, right? And this would have to be 20, right? Because we're decreasing it by 4, so then we're gonna get 20. But from here you can see that like there's no possible way to get like 22, right? You can't decrease one of the 8s by 2 to get 6. That's not allowed. So we can't get that, and there's nothing else you can really do. So then you can see that 22 is definitely not possible. And then all the other ones were included, so all of those have to work. So we didn't miss anything else. So then all of our possible distinct sums is just going to be all of this. And then you just sum this together. I don't know. I like to like group the ones that add up to like multiples of 10 together and just like add that together. So like 14, 16 gives me 30, 20 gives me 50, 10 gives me 60, 8 and 12 gives me 20, add to my 60 is going to be 80. And then 6 and 24 is going to give me 30, add that to my 80, that's going to be 110. And then plus my 18, that's going to give me 128. And then, yeah, we can see our answer is 128. Anything you want to say for that one, Bill?
Uh, well, I was also thinking of a way where you can just like um you could just like do how should I say this? Like just find the sum of all of the one like they not necessarily distinct ones, like just all of the possible values, and then just subtract the repeated ones. Subtract the repeated values so that all of them end up being distinct. Does that make sense?
Yeah. I don't know. I still feel like it would be a little bit weird, like finding. I mean, I guess it's still possible, but like you still have to find like all the ways, like for each sum, like how they can be repeated, right?
Right. Yeah. I mean, if you think about it, it's kind of hard to like repeat something, right? I mean, it's definitely possible. It's still kind of hard to repeat something. I feel like to like get two numbers that like end up being repeated.
Hmm. Maybe, yeah. Or yeah, I mean, yeah, you could probably also do it like that. Okay, well, it is 8:02.
Hmm.
So, yeah, we're gonna be ending it here for today. So, thank you for coming to our Mathcounts meeting, and yeah, we will continue from here next week. Um, so yeah, thank you for coming, and